Module 3, DNP3 Layered Architecture, How Reliable Communication is Achieved. ASH/NAPSRI 3.1 Rationale for Layered Protocol Design. DNPP3 is architected as a layered protocol to isolate responsibilities, improve reliability, and accommodate the realities of utility communication channels. Utility networks are inherently imperfect. Noise, latency, intermittent connectivity, and bandwidth constraints are expected operating conditions rather than exceptions. A layered architecture allows DNP3 to decouple application logic from physical communication media, implement reliability mechanisms independently of user logic, scale across serial, radio, and IP-based networks, preserve deterministic behavior under adverse conditions. DNP3 employs a three-layer model with a tightly integrated transport function embedded within the application layer. ASH 3.2 Overview of DNP3 Layers. DNP3 communication is structured into the following logical layers. 1. Application layer. 2. Transport function within the application layer. 3. Link layer. 4. Physical media external to DN3 specification. Each layer performs a distinct role while interacting in a strictly defined manner with adjacent layers. ASH 3.3 Application layer. Role and responsibilities. The application layer is responsible for protocol semantics and user-visible behavior. It defines function codes, read, write, operate, freeze, time sync, etc., object groups and variations, fragmentation of large messages, event classification and reporting, application-level confirmations and error responses. This layer interfaces directly with the DNP3 user layer, which contains the master or outstation's internal database and control logic. Application Protocol Data Units, APDUs. The application layer exchanges data using Application Protocol Data Units, which consist of application control field, function code, object headers, and object data. APDUs may exceed the maximum frame size supported by the link layer, requiring fragmentation. 3.4 Embedded Transport Function. Purpose of the transport function. DNP3 does not implement a standalone OSI transport layer. Instead, it embeds a lightweight transport function within the application layer to segment large application messages into smaller units, reassemble received segments into complete application fragments, maintain message ordering and completeness. This design minimizes overhead while preserving reliable message delivery. Transport segmentation. Key characteristics. Each transport segment consumes 1 octet of overhead. Maximum payload per link frame is 249 application layer octets. Transport headers include first fragment indicator, final fragment indicator, sequence number. This enables detection of missing or duplicate segments during reassembly. 3.5 Application layer fragmentation. Fragment size determination. Application layer fragmentation occurs when an APU exceeds the receiving device's buffer capacity. Typical fragment sizes range from 2048 bytes, 4096 bytes. Fragment size is negotiated implicitly through device capabilities and configuration. Operational considerations. Large fragments reduce protocol overhead, but increase retransmission cost in noisy environments. Smaller fragments improve reliability at the cost of increased frame count. Fragmentation strategy directly affects system performance and reliability in field deployments. 3.6 Link layer. Link layer responsibilities. The link layer is responsible for frame-level reliability and device addressing. Its primary functions include frame delimitation and synchronization, error detection using CRCs, duplicate frame detection, optional link layer acknowledgements, source and destination address handling. This layer ensures that frames delivered to the application layer are valid and correctly ordered. 3.7 Link layer frame structure. Each DNP3 link layer frame consists of synchronization bytes, frame alignment, length field, frame size excluding CRCs, link control field, destination address, source address, data payload, cyclic redundancy check CRC fields. CRC protection is applied to the header, each block of 16 data octets within the payload. This block-based CRC strategy significantly improves error detection on noisy links. 8 Addressing model. Device addressing. DNP3 supports up to 65,520 unique device addresses within a communication domain. Addressing enables one-to-one communication, multi-drop networks, peer-to-peer exchanges. Special addresses. Reserved addresses support all-call messaging, broadcast to multiple devices, future protocol extensions, special operational scenarios. Each DNP3 device must maintain a unique address within its network scope. 3.9 Link Layer Confirmation Mechanism. Optional confirmations. The link layer can request confirmation that a frame was successfully received. This mechanism increases reliability on unreliable media, introduces additional latency and traffic. As a result, link layer confirmation is optional and selectively used depending on network conditions and system design. HABSNetter. 3.10 Interaction between layers. The layered flow of a typical DNP3 transaction is as follows. 1. User layer requests an operation. 2. Application layer constructs APDU and fragments it. 3. Transport function segments fragments into frames. 4. Link layer transmits frames with CRC protection. 5. Receiving link layer validates frames. 6. Transport function reassembles segments. 7. Application layer processes complete fragments. 8. User layer updates database or executes control logic. Each layer performs its role independently while preserving end-to-end protocol correctness. Nabjor 3.11 Architectural Outcomes. The layered architecture of DNP3 enables reliable communication over adverse field networks, deterministic master-outstation interactions, efficient use of constrained bandwidth, scalability from small serial links to IP-based WANs. By embedding reliability, segmentation, and semantic control into discrete layers, DNP3 achieves a balance between robustness and efficiency required for utility-grade automation systems.